The quantum world is a realm of profound and often counterintuitive phenomena, but few are as perplexing and subtle as the concept of bound entanglement. Unlike the more familiar, free entanglement that fuels quantum teleportation and superdense coding, bound entanglement is a form of quantum correlation that cannot be transformed into a pure, maximally entangled state through local operations and classical communication, LOCC, even when multiple copies are available. This makes it a particularly elusive and fascinating resource to study. For years, detecting these subtle correlations was a significant challenge, limited largely to lower-dimensional systems like 3-circled times 3 and 2-circled times 4. However, a remarkable breakthrough has been achieved: the successful construction of linear maps capable of detecting bound entanglement within 4-dimensional quantum systems, 4-circled times 4. This advancement represents a pivotal step forward in our ability to characterize and understand the complex geometry of entanglement in higher dimensions, unlocking new possibilities for quantum information processing. To appreciate the significance of this breakthrough, it is essential to understand what bound entanglement is and why it is so difficult to detect. The concept was first introduced in 1998, identifying a puzzling form of quantum correlation that is genuinely entangled but from which no pure entanglement can be extracted. Despite this uselessness in one sense, bound entanglement has proven to be a valuable resource for a variety of quantum information tasks, including quantum key distribution, quantum metrology, and channel discrimination. The standard method for detecting entanglement in many scenarios is the positive partial transpose, PPT, criterion. A state that has a positive partial transpose is called a PPT state, and while all separable states are PPT, there exist entangled states that are also PPT. These are the very bound entangled states that researchers are striving to detect, and they often lie in a gray area where standard methods fail. The recent research, spearheaded by Mazhar Ali at Islamic University and colleagues, and detailed by Istvan Martin, Erica Benet, and Thomas Vertisi, tackles this problem head-on by constructing a new family of positive, but not completely positive, linear maps. These maps act on a 4-dimensional Hilbert space, providing a more sensitive probe for entanglement. The key lies in their mathematical structure. They are powerful enough to reveal entanglement that would otherwise remain hidden, a necessity that existing generalized Choi maps failed to meet when tested on known bound entangled states in 2-circled times 4 systems. The novelty of this work is multifaceted. One line of research, focused on the 3-party prepare and measure scenario with 4D quantum messages, has introduced a class of linear correlation witnesses capable of detecting bound entanglement. A critical advantage of these new witnesses is their experimental practicality. They require only qubit rotations on the sender's sides and simple product qubit measurements with binary outcomes on the receiver's side. Furthermore, they do not require post-processing of measurement outcomes depending on the receiver's input, making them more straightforward to implement in a lab. This research has yielded some compelling quantitative results. One of the most impressive findings is that a well-known 2-quart, 4D, bound entangled state with a positive partial transpose can be mixed with up to 40% isotropic noise and still be successfully detected by the prepare and measure witness. This demonstrates exceptional robustness and suggests that these witnesses could be invaluable for entanglement verification in realistic quantum devices, which are inevitably affected by noise and imperfections. By comparison, other methods only tolerate up to 28.69% noise in similar scenarios. The research also clarifies that these new maps and witnesses can detect bound entangled states in dimensions beyond 4, up to arbitrary D dimensions, and can even outperform the computable cross-norm realignment, CCNR, criterion for D greater than 4. This progress in detection is complemented by significant advances in the creation of 4-dimensional entanglement itself. Researchers have developed deterministic protocols for generating arbitrary 4-dimensional 2-qubit and multi-qubit maximally entangled states. These protocols leverage hybrid polarization spatial states of photons to encode qubits, offering advantages in resource saving and noise resistance. Using linear optics elements and single-sided cavity NV center systems, they have achieved near-unity fidelities for these entanglement generation schemes. Other approaches, based on heralded schemes with hybrid photon emitter systems and waveguide-mediated scattering, have also demonstrated the ability to generate random 4D 2-qubit maximal entanglement, with potential for extension to n-qubit systems. The Kerr effect is also being explored for generating high-dimensional entanglement for qubit systems, offering schemes with high success probabilities and robustness against photon loss. These theoretical and experimental advances are converging. The development of robust methods for both the creation and detection of four-dimensional entanglement paves the way for practical applications. The creation of high-fidelity 4D entangled states is a prerequisite for the quantum communication protocols that could one day benefit from the extra dimensionality. Simultaneously, the new detection methods can ensure the quality of these states. The detection of bound entanglement is of particular interest because it was previously thought to be a purely negative resource, but its detection in higher dimensions suggests it may be more useful than originally thought, particularly for information processing where strong correlations are not always required. In addition to these prepare and measure and linear map approaches, other avenues are being explored for detecting bound entanglement in 4D systems. Research has shown that sets of mutually unbiased bases, MUBs, can be used to construct entanglement witnesses. For a four-dimensional system, it has been proven that 3 MUBs are necessary and sufficient to detect bound entangled states, and new families of bipartite bound entangled states in a 4x4 system have been found using this method. This not only confirms the existence of such states, but also provides an experimentally friendly detection approach that requires significantly fewer measurements than full quantum state tomography. The successful detection of bound entanglement in 4D systems is a testament to the power of mathematical physics and its ability to reveal the hidden structures of the quantum world. It clarifies the geometry of partially transposed positive entangled states, providing new analytical insights into their structure and expanding our capabilities beyond the previous limitations. While the current method identifies bound entanglement, future work will focus on quantifying the amount of entanglement present and comparing its efficiency with existing techniques. As researchers continue to refine these approaches, we move closer to a future where the full potential of high-dimensional quantum systems can be harnessed, not just in theory, but in robust, practical quantum technologies.